Hello, my name is Farzad. I'm working in the Energy Conversion and Integration Trust under the supervision of Dr. Chris Edmonton. Today I want to run an experiment in order to evaluate the stability in real time in microgrid and also measure the complexity level in the system in a modern distribution system. Modern distribution systems are highly penetrated by renewable energy resources, power electronic-based component, and control loops, so they are highly prone to instability issues. So we have to monitor the dynamical behavior in the distribution system. The test study we're working on is the Green Energy Hub, which is designed by the Freedom System Center in the North Carolina State University. As you can see in the monitor, this system consists of 3 SSTs connected to the microgrid in the distribution system. The input of the distribution system is 7.2 kilovolt and the output of each SST is 120 volts. So at the end of this, at the load side of the SST, we have a 3-wire single phase system. For each SST, for each solid state transformer, we have a rectifier and then high voltage link DC, and then the voltage through a dual active bridge, which is a DC to DC converter. 3.8 kilovolt is converted to 400 DC volt, and after the low voltage DC link, we have the inverter in which 400 volt is converted to 120 volts. So at the load side of the solid state transformer, we have a single phase system but 3 wires, in which one of the wires is neutral. In this experiment, we have connected 3 real-time processors. We have 15 Mario processor from the National Instrument. As you can see from this picture, 3 SSDs are all connected to the processors, and processors are connected to the LabVIEW interface. So we can see the result in real time in LabVIEW. Okay. So we have already imported the data in the hard drive in the real-time processors, and processors are connected to the SSD. What we measure here is the voltage at the load side. We have 4 scenarios in the distribution system in order to test the complexity and the stability measurement. In the first scenario, we have load switching at the AC load side of the SSD. The nominal load of this SSD in this Green Energy Hub is 5 kVA. So in this scenario in which we have load switching at the load side, another 5 kVA load is connected at 1 second and then is disconnected at 2 seconds. So in other words, the system is operating in the load condition, which is 2 times greater than the nominal loading condition. In the second scenario, we have considered a high impedance fault at the grid side of the SSD. So we want to see the dynamical behavior of the system in the high impedance fault, in which we don't have that's really an important thing. In the high impedance fault, we don't have a high level of current. So typical protection devices like high current relays cannot or are not even enabled to detect this kind of dynamical behavior. In the third scenario, we're considering an islanding condition at 1 second. We have considered a switch at the grid side of the SSD. At 1 second, the SSD is disconnected from the grid and goes to the islanding condition. In this condition, in islanding condition, there is a DG in distributed generator. We have considered a constant current source as a DG at the low voltage DC link. So after 1 second, the system gets to the islanding mode and the DG is supplying power to the load. In the fourth scenario, which is a plug and play condition, the purpose is to see the impact of plug and play or an emergent dynamics in SSD 1 to SSD 3. So the plug and play condition occurs here in this point of the microgrid, and the measurement is taken this side at the load side of the SSD3. In other words, we want to see the impact of plug and play in one point in the grid to the other points in the grid. Let's go back to the experiment. In this part of the lab, you can see 15 Marios. There are real real-time NI processor. So I have already imported data in 3 MIRIOs for islanding condition, fault, and load switching. So from here, the data are sent to the layout I have already designed in the lab view for each condition. So I'm considering 3 conditions for now. Like I said, islanding, fault, and load switching, and I can see the results in these 2 monitors in real time. Intentionally, I have increased the step time here from 2 milliseconds to 100 milliseconds in order to make the visualization better, and in order to the main purpose. The reason why I increased the step time here intentionally is that I want to make the simulation slower, because if I choose 2 milliseconds here, all the simulations will run in real time, which is 2 milliseconds, and it's really fast. In order to make a better visualization of the results here, I have increased the step time from 2 to 100 milliseconds. If we run the system, you can see the dynamical behavior of the system in 3 parts. This part reflects the load switching conditions. This part, these 6 figures here, is related to the high impedance fault condition, and this area is dedicated to islanding condition. So let me save the model. These 3 figures over here and this part are showing the phase space is the visualization of dynamical behavior of the system, because in the real-time target it's impossible to show the system in 3-dimensional phase space. I am using 3 2-dimensional phase spaces, so X, Y, XZ, and YZ. Like I said, I want to mention again that this part is for the load switching, this part for the high impedance fault, and this part for islanding condition. As you remember, at 1 second, the system is operating in a load condition which is 2 times greater than the nominal load. So 5 kVA load is connected at 1 second and is disconnected at 2 seconds. For the high impedance fault, the system goes to the fault condition in 1 second. So at when you're considering 2 milliseconds of time step, it should go to the fault condition at 500. This is the number of sample. You can see that as soon as it gets to 500, it goes to the high impedance fault condition. You can see both entropy and complexity are increasing here, and the phase space over here, after the fault is clear, goes back to 1 single point, as we expect as the phase space for the normal system. And here the system goes to the islanding condition. You can see after the 500, at which the system goes to the islanding condition, both entropy and complexity increases. And also, if you're considering these parameters associated with the phase space, number of dimension, filtering level, you can see the change at the time islanding or fault or load switching occurs. So these results validate our proposed technique, because they have been able to detect dynamical changes in the system with 0 time lag between the event and response. In other words, the calculations of the complexity are all in real time.